Not going to talk too much about the energy equation. We won't really use it in this class. I do want you to take a look at it and see it, particularly in the context of what we just did. You can see it's very, very similar to the momentum equation. So we have temperature here as our independent variable, and the time rate of change in temperature depends on the amount of temperature in neighboring regions that's being carried in by fluid. So, you can carry higher temperatures in or carry higher temperatures away. Same in any of the three directions. That type of heat transfer is called convection heat transfer. You're going to learn all about that in the spring semester when you take heat transfer. So convection heat transfer is represented by these three terms that are where your temperature is being moved around by the moving fluid. This is conduction heat transfer. This is the heat being transferred by direct molecular contact. So molecules are actually touching each other and vibrating differently and causing energy to transfer from one to the other and changing temperatures. Internal heat generation, this piece on the end, lots of problems don't really have that, but there are some that do. If you're talking about living tissue, then they can generate their own heat, and they can't deal with that. Chemical reactions, of course, which is what biological systems are using, can generate heat. You can fire some kind of radiation inside an object, like with a laser or a microwave, and that can generate internal heat. So those things are, definitely less common. But these two, conduction and convection, they are very, very, powerful modes of heat transfer, and you'll study them extensively next spring. But we won't really get into this equation because the systems we're going to study are almost always isothermal in this class. I mean, they're very rarely do they have significant temperature differences in different parts of the space of the problem. So this is really when there is temperature differences in the spatial dimension. Of course, it's worth mentioning we are still going to continue to use the control volume version of the first law. We've used that in our integral analysis many times already. We continue to use it. But that just says, that this one you're well familiar with from thermo, change in energy of the system, Q dot, W dot, mass flow in, mass flow out, enthalpy, all that. We've been doing that plenty. So we will still use this, but that's for a macroscopic control volume. That's not a differential equation. This is the differential equation that if you were to go on to study computational fluids that involved heat transfer, you would add this equation as your sixth equation that would allow you to determine temperatures in the context of moving fluids.